Welcome to section 5.2, the characteristic equation. In this section, we're going to expand our knowledge of eigenvalues and come up with a special scalar equation, which is known as the characteristic equation. Before we get started, I'd like to remind you of a few things. We are going to come up with a method that allows us to find eigenvalues for a square matrix. This was briefly discussed in the previous section, but this comes up with a more extravagant way to find these eigenvalues. So before we proceed, remember that a matrix is not invertible if and only if the determinant is 0. And this was discussed in section 2.3. So you might want to go back and look at that invertible matrix theorem. Another thing is that the scalar lambda is an eigenvalue if and only if this equation here has a non-trivial solution. So putting the two together to find the eigenvalues, we must find when the determinant is equal to 0. Now, this notation here is for determinant. This is the determinant, not the absolute value. So this basically says the same thing as the box on the top of page 277. So it's just a different way of looking at it, which I think is a little more simple. So the equation that we get from finding when the determinant is equal to 0, that is called the characteristic equation. And this piece here is the characteristic polynomial. So obviously, if there's an equal sign, then that's an equation. Otherwise, it's just the characteristic polynomial. The eigenvalues are the roots of this characteristic polynomial. So basically, you find the roots, and those are the same as the eigenvalues. Sometimes we have an exponent involved, so we talk about the multiplicity of the eigenvalue, which is the same as the multiplicity of the root. So for example, if this here is my characteristic equation, then lambda is equal to 3 and 4. Those are the eigenvalues, where this eigenvalue has a multiplicity of 2, and this eigenvalue has a multiplicity of 1. Let's go ahead and look at the first example. Sorry for this typo. This is the question. This is your first step, so I apologize for that. So we want to find the characteristic equation of that matrix and use it to find the eigenvalues. So to solve, your first step is to form A minus lambda I and find the determinant of that. So again, remember the notation is this. So this is find the determinant of A minus lambda I. So remember from the previous section, matrix A is this matrix. Minus lambda I is lambda times the identity matrix, which ends up being this matrix here. So when I subtract these two matrices, I end up with 1 minus lambda, 4, 2, and 3 minus lambda. And I want to find the determinant of this. To find the determinant of this, I will multiply these two values and subtract the product of these. Okay, well, now I can leave it like this, but it's not ideal. So instead, what I want to do is FOIL this out. and then subtract the 8. And when I FOIL this out, I get 3 minus 4 lambda plus lambda squared minus 8. Combine like terms, put it in standard form, and I end up with lambda squared minus 4 lambda minus 5 is equal to 0. This here is my characteristic equation. Okay, now this characteristic equation, and that's a polynomial, what I want to do from here, so once I find the characteristic equation, now I want to use it to find the eigenvalues. So I want to solve this equation, and this is a quadratic. Remember, with quadratic equations, there are lots of different ways you can solve it. The two most common would be to factor, if it's factorable, and if it's not, then use the quadratic formula to solve the quadratic equation. In this case, I can factor, and I do remember factoring. Hopefully you do as well. That polynomial or quadratic equation factors into lambda minus 5 times the quantity lambda plus 1. If I set this equal to 0, then we find that lambda is either equal to -1 or 5. Not only are these the roots of that polynomial equation, but these are also the eigenvalues of the matrix. And that's all there is to it. See if you can pause this and solve this on your own. I'm going to let this be called matrix A. So in order to find the eigenvalues, the first thing I'm going to do is identify my characteristic equation. And I'm going to do that by solving this. So A is the matrix listed there, minus lambda I. I'm just multiplying lambda by 1 at that diagonal. So this becomes 2 minus lambda, 3, 3, and -6 minus lambda. And we want to find the determinant of this. At some point, some of you may be able to skip this step and jump to this step right away. Some of you will have to write it down. Either way is perfectly fine. Okay, so to find the determinant of this, I'm going to multiply the diagonals. Then I'm going to subtract this product here. Okay, so as I continue, I'm going to FOIL this. When I FOIL that, I get -12 plus 4 lambda plus lambda squared minus this 9 here. So standard form and my characteristic equation become lambda squared plus 4 lambda minus 21. That's my characteristic polynomial. When I set this equal to 0, this is my characteristic equation. Okay, now the question here is to find the eigenvalues. So once I have my characteristic equation, then I find the roots of that. And I do that by factoring, quadratic formula. You can complete the square if you want. It doesn't matter as long as you find those roots. So this polynomial can be factored. In fact, it factors to lambda plus 7 times lambda minus 3. This is equal to 0. So we find that lambda is equal to -7 and 3. So if the determinant of this is equal to 0, then lambda is equal to -7 and 3. So these are my eigenvalues. So we have found the eigenvalues of 2x2 square matrices. Let's pick it up a notch and find the eigenvalues and characteristic equations of larger matrices. Take this one, for example. Now, before I go on, I didn't include it in this video, but Theorem 3 on page 278 has properties of determinants. You may want to review that a little bit because it may be helpful. But remember, when we are doing this, if we want to find the characteristic equation, we want to find the determinant of A minus lambda I. Okay, now in our case, remember that you're going to take these diagonals and multiply those. You're going to take that minus lambda times I, so it's these diagonals minus lambda. So this is equal to 5 minus lambda, and I'm just going to go down the column, negative 2, 3 minus lambda, down the column, 5 minus lambda, and then 1 minus lambda. Okay, now there is a property of determinants in this theorem that states the diagonals of a triangular matrix will give you the determinant. So if I want to find the determinant, all I need to do is find the product of the diagonal. You may or may not remember that from previous sections. So I end up multiplying each of these values found at the diagonal. So that is the determinant. Remember, if I set this equal to 0, then that will give me the characteristic equation. Now, I can also notice that I have some common factors. So I can write this as 5 minus lambda quantity squared, 3 minus lambda, and 1 minus lambda. I would accept that. But then you could also FOIL this all out, multiply it all out, come up with the polynomial, so the characteristic polynomial as well. Just for the sake of this video, we'll go ahead and say this is the characteristic equation, but of course if you want to expand that, you are certainly able to. In this example, now I've given you the characteristic equation of a 6 by 6, or I'm sorry, the characteristic polynomial of a 6 by 6 matrix. It is this here. And I want to find the eigenvalues and their multiplicities. Okay, well, so now what we're going to be doing is working backwards a little bit. So now I know the polynomial and I want to find the eigenvalues, or I want to find the roots of the polynomial. In algebra, if you wanted to find the roots of the polynomial, you would factor this. And that's exactly what we're going to do. So remember, steps of factoring, the first thing you want to do is find the greatest common factor. Of those three terms, the greatest common factor is lambda to the power of 4. If you have 3 terms here, you need to make sure you have 3 terms here. Lambda to the 4th times lambda squared is lambda to the 6th, minus 4 lambda minus 12. Okay, well, now this can be factored. I want to make sure I keep that GCF, and then I'll factor that polynomial there. So factors of 12 that combine to be a negative 4. Remember, if this is a negative, you need one of each sign. One's positive, one's negative. You want the larger of the two numbers to be negative, so you will use a positive 2 and a negative 6. So these are my factors. If I set this equal to 0, then I will find the roots, and this will in turn allow me to find the eigenvalues. Well, lambda to the 4th equals 0. is when lambda is equal to 0. Lambda is equal to -2, and lambda is equal to 6. This has a multiplicity of 4, where each of these have a multiplicity of 1, since these have an exponent of 1 and this has an exponent of 4. Now, if I wanted, I could say that lambda equals 0, 0, 0, 0, -2, and 6. Because if this is a 6 by 6 matrix, then I should have 6 eigenvalues, but because of the multiplicities, we only need to write them once, unless stated otherwise. I'm going to conclude this section with another addition to the invertible matrix theorem. Remember, if you see IMT, it's referring to the invertible matrix theorem. These are things that we have discussed but not stated explicitly. So the number 0 is not an eigenvalue, and the determinant of A is not 0. Okay, so more of these are equivalent in the invertible matrix theorem. That concludes section 5.2 and really concludes our work in chapter 2. The end is, or I'm sorry, chapter 5. The end is near.